It's June 23rd, 1998, and what Andy Ulmer, a farmer from Columbus, Nebraska, is recording from his window will forever change the way the world views tornadoes. That day, the conditions were perfect for hell to break out. The year 1998 will go down as one of the most aggressive in modern tornado history in the United States. From the first days of January, the air itself seemed to carry an invisible electrical charge, a harbinger that something unusual was brewing in the upper layers of the atmosphere. In February, tragedy struck Florida. The so-called President's Day outbreak left more than 40 dead, making it the deadliest event in the state's modern history. It was just the beginning. In March, the cold north was still holding, but Minnesota was the scene of a completely unseasonal outbreak. Supercells and tornadoes formed where it used to snow at that time. But the real terror came in April. In the heart of Dixie Alley, Alabama and Tennessee was struck with brutal force by two tornadoes classified as F5, the highest category on the Fujita scale. With winds estimated at over 400 kilometers per hour, these monsters not only leveled homes, they ripped the very foundations from the ground and lifted asphalt from roads. Dozens of lives were lost. The ground, blackened by debris, looked more like a battlefield than a residential area. The National Weather Service began issuing warnings more frequently. The atmosphere was charged. The polar jet stream fluctuated erratically, and tropical air masses surged from the Gulf of Mexico, pushed by an unusually warm ocean. All signs indicated something big was still to come. In May, an alarm bell rang in a place where no one expected it, the northeastern United States. For the first time in years, a high-risk warning was issued for that region. An anomaly and a confirmation. The 1998 tornado season wasn't just active, it was breaking the rules. And then June came. Nebraska, located in the heart of Tornado Alley, is a state accustomed to viewing the sky with suspicion. The vast open plains, with few geographical barriers, make this region the perfect setting for violent storms to develop and evolve unchecked. But even for longtime residents, June 1998 was unsettling. The days passed between humid heat and strangely quiet skies, as if the atmosphere were holding its breath. The grass grew faster, the animals behaved erratically, and every weather report spoke of increasing instability. But beyond the sensations, the data was clear. The CAPE index, a measure of how much energy is available in the atmosphere to develop thunderstorms, began to reach extreme levels. In the days leading up to June 23rd, levels above 4,500 joules per kilogram were recorded. Simply put, the atmosphere was so charged that a single spark could trigger a supercell thunderstorm. Furthermore, dew points, another key indicator, remained close to 24 degrees Celsius, extremely high values for the center of the country. This meant that the moisture in the lower layers of the atmosphere was more than sufficient to fuel long-lived storms. The third, and perhaps most critical ingredient, was the low-level jet, a nighttime phenomenon that accelerates winds in the layers closest to the ground just after sunset. This jet, invisible to the naked eye, is like a conveyor belt injecting warm, humid air from the south into atmospheric hotspots. Its sudden appearance can mean the difference between a severe storm and a destructive tornado. And that was exactly what happened on the afternoon of June 23rd. A low-pressure system began moving from the Rocky Mountains toward the central United States, positioning itself ideally over Nebraska. At the same time, a dry line, a natural boundary between moist air from the east and dry air from the west, stretched from northern Kansas to South Dakota. These dry lines are notorious among meteorologists. They are flashpoints, where opposing air masses collide and forcefully rise. When temperatures exceeded 26 degrees Celsius and humidity reached tropical levels, the outcome was almost inevitable. Shortly after 6 p.m., thunderstorm cells began to form over eastern Nebraska. But this was no ordinary storm. One of those cells, located southwest of Columbus, began showing signs of cyclonic rotation. Doppler radars detected strong reflectivity, with a hook signature at the southern end. Classic signs of a tornadic supercell. As meteorologists watched with growing anxiety from their screens, rural residents faced a very different reality. From the ground, there were no diagrams or technical data. Just a sky darkening beyond natural range, and a silence broken only by the buzzing of insects, until the wind arrived. At 6:35 p.m., the first tornado warning was issued for Platte County. The public was warned. A severe thunderstorm with tornadic potential is approaching the Columbus area. But for many, that warning came when it was already too late. The supercell had fully matured. Within minutes, north of the small town of Duncan, a funnel began to form. The system's first tornado touched down. It was weak, later classified as F1, but it was just a rehearsal. The city of Columbus was spared by minutes. The storm seemed to have disorganized as it crossed the urban outskirts. But as so often happens with these systems, the worst had yet to begin. Just 5 kilometers ahead, the storm regrouped. New warm air currents moved in from the south, shear increased, and rotation within the main mesocyclone intensified. The result would be one of the most extraordinary, intense, and photogenic tornadoes ever recorded. And across the field, Andy Ulmer, unknowingly, already had his video camera on. 6:45 p.m. The sun was slowly setting over the Nebraska plains, dyeing the sky shades of amber and purple. To the naked eye, the scene was almost idyllic. But for those who knew how to read the sky, this was no ordinary sunset. It was the backdrop for something far more dangerous. The supercell thunderstorm that had passed through Columbus without causing any visible damage was now showing unmistakable signs of reorganization. On Doppler radar, the Hooke signature was intensifying, and meteorologists were beginning to use a term they rarely use lightly: tornado imminent. On land, the signs were just as clear: restless animals, a sudden breeze that became erratic, the sudden drop in temperature, and then the sound. It wasn't thunder, it was deeper, steady, and deep, like a freight train approaching from the horizon. But there were no tracks nearby. Only fields, corn, and farms. The tornado formed visibly shortly after 6:47. It wasn't a sudden appearance. First, a nearly invisible vortex began to form over an open field north of Duncan. Dust, vegetation debris, and a faint condensation in the air began to spiral. Then the funnel descended decisively from the cloud base, and within seconds, it was in contact with the ground. The National Weather Service would later confirm that this was the system's second tornado. The first, weaker one, had already dissipated. This new vortex was different in nature. It was wider, more organized, and it was moving in a clear direction, northeast, toward the rural area north of Columbus. It was then that 3 different witnesses in separate locations began documenting the event, unaware that their recordings would go around the world. From a farm north of Columbus, Kent Sunderman watched the sky with growing anxiety. He wasn't a meteorologist, but he knew enough. The change in cloud color, the murmur of the wind, and the presence of hail were unmistakable signs. He watched the funnel descend and began recording. His camera captured the first moments of complete condensation. "Oh no, it's touching down. I hope no one gets hurt," he exclaimed. While in the background, a second, smaller vortex could be seen. A satellite tornado swirling around the main one. The appearance of satellite tornadoes is rare and suggests a particularly powerful storm. The weaker vortex seemed to orbit the larger one like a turbulent moon, spinning in an ominous ballet over the fields. About 5 kilometers northeast of Sunderman's position, Arland Wilkie also had his video camera ready. He had been following the storm's progress from his barn, and when the tornado appeared on the horizon, he wasted no time. What his lens captured was a stunning image: a fully formed vortex, about 400 meters wide, moving with apparent slowness, although in reality it was moving at more than 30 kilometers per hour, and devastating everything in its path. The trees, Reuben's house. "There'll be nothing left," he cries in despair. The tornado swallows entire farms in a matter of seconds. Debris clouds rise hundreds of feet. It's not just a funnel of condensed air. There are fragments of wood, roofs, machinery, and trees spinning at hellish speeds. The scene is as intense as it is hypnotic. The earth seems to vibrate with each turn of the vortex. But the most iconic footage of all was about to begin. Andy Ulmer, a Columbus farmer, had just returned from the airport. His house was right in the tornado's path. From his window, he saw the approaching funnel and he didn't hesitate. He grabbed his camcorder and started recording. The images he captured are now considered one of the best home video recordings of a tornado ever made. The clarity, the close-up, the drama of the scene. Everything comes together in a piece that is now studied in documentaries, universities, and meteorological centers. "Look at the whirlpools. Oh my God, it's coming right at us," Andy shouts. His voice is laced with a mixture of wonder and fear. The tornado is approaching, changing shape with every moment. In seconds, it transforms from a classic funnel into a monstrous wedge, with a base so wide it seems to devour the horizon. His wife Susan appears in the recording. "Andy, come to the basement," she pleads, but he can't tear his eyes away. It's not stubbornness. It's a mixture of fascination and shock. And then he lets loose with the phrase that would become immortalized in the popular culture of tornado documentaries. "Susan, get me my pants." A line as absurd as it is human. Amidst the chaos, Andy tries to hold on to an everyday act. It's a scene of tension, unintentional humor, and profound vulnerability. Outside, the tornado continues to grow. It changes shape again, becoming narrower, like a rope, but without losing its intensity. The rope, although deceptive due to its thin shape, can be even more dangerous, with concentrated winds reaching extreme levels. And then something happens that would completely change the outcome. The tornado veers sharply west, missing Andy's house by just a few hundred yards. It's an unusual turn. Most tornadoes follow more stable paths, but this one, for reasons still unknown, decided to alter its course just before the direct hit. That small detour saved a life, and it allowed the world to see the face of the tornado through Andy's lens. At 7:05 p.m., the tornado began to slowly dissipate. In total, it had been on the ground for just over 20 minutes, but in that short time, it devastated fields, barns, and rural structures, leaving a path of destruction more than 5 miles long. The National Weather Service officially classified it as an F2, with estimated winds between 182 and 250 kilometers per hour. But many experts, after analyzing video footage, the tornado's behavior and damage in isolated areas, contend the tornado could have been stronger. Perhaps an F3, even an F4, if it had hit more resilient structures. What's undeniable is that the storm wasn't over yet. Over the next 2.5 hours, it would produce 4 more tornadoes, spreading its deadly signature across eastern Nebraska. But the second tornado, the one in Columbus, was the one that remained etched in the collective memory. Not because of the number of victims. Fortunately, there were no fatalities, nor because of the extent of the material damage, but because someone looked it straight in the eye and didn't let go of their camera. When nature decides to unleash its full fury, it does so through mechanisms that, although invisible to the naked eye, obey perfectly defined physical laws. And yet, despite our modern technology and decades of research, tornadoes remain, to a large extent, an indomitable mystery. The Columbus, Nebraska event on June 23, 1998, left us with more than impressive images. It offered science an unparalleled case study. A supercell thunderstorm is not just any storm, it's a higher-order phenomenon. While ordinary thunderstorms are composed of cells that grow, precipitate, and die within minutes, a supercell is a self-sustaining system. It organizes itself like an atmospheric engine, where each gear feeds the next. Moisture, heat, rotation, and shear combine to create a machine of destruction. At the heart of that machine is a hidden vortex, the mesocyclone. This is a rotating area several kilometers wide within the storm itself, and it's there that the most violent tornadoes are born. The Columbus tornado was undoubtedly the product of a well-developed mesocyclone, one that persisted for more than 3 hours as the supercell moved across eastern Nebraska. In the days leading up to the event, the atmosphere was already set. What was missing was a spark. And that spark was a combination of 3 key ingredients: First, a dry line, a boundary between moist air from the east and dry air from the west, served as a starting point for the storms. This front caused warm, moist air to rise rapidly. Second, the CAPE, convective available potential energy, index exceeded 4,500 joules per kilogram. For meteorologists, these values indicate extremely unstable conditions, ideal for explosive storms. Third, and perhaps most crucial, was the low-level jet stream that intensified at dusk. This jet stream, invisible from the ground, consisted of strong winds blowing from the south at speeds reaching 90 kilometers per hour at just 1,000 meters above sea level. This abrupt change in wind speed and direction with height is known as vertical wind shear. Wind shear is the true magic ingredient of tornadoes. Without it, storms can be intense, but they won't rotate. With it, a kind of invisible horizontal vortex forms, which, when tilted by the storm's updraft, becomes vertically rotating. And if the mesocyclone intensifies enough, a tornado appears. In the case of the Columbus tornado, the recordings allowed us to observe each phase of its structural evolution with a level of detail rarely seen. Phase 1, formation funnel visible. The funnel slowly descended from the base of the cloud. At first, it was thin, almost tentative, but winds on the ground began to kick up dust, confirming that it was already in contact with the surface. Phase 2, maturity, wedge shape. The tornado then expanded laterally. It transformed from a thin cylinder into a colossal wedge of dark clouds and dust. At this point, it was estimated to be over 400 meters wide and strong enough to uproot trees and destroy structures. Phase 3, occultation, precipitation envelope. At times, the supercell's own rainfall engulfed the tornado, making it difficult to see. This is one of the most dangerous characteristics of supercells. They can hide the tornado within their core of intense rain. From a distance, it may look like just another storm, but inside lurks a killer. Phase 4, stretching, rope shape. Eventually, the tornado began to lengthen and become thinner. This wind-up phase may seem harmless, but it's deceptive. The winds can remain extremely destructive, concentrated in a narrower area. One of the most fascinating aspects of the Columbus tornado was its erratic behavior. Unlike other tornadoes that follow a more or less straight path, this vortex suddenly shifted westward in its final phase. This unexpected turn narrowly missed Andy Ulmer's house by just a few hundred meters. Why did he change course? There are several theories. One suggestion suggests that the tornado interacted with a rear flank downdraft, RFD. A gust of dry air descending from the rear of the supercell. This downdraft can act as an atmospheric rudder, pushing the tornado in unexpected directions. Another possibility is that the tornado was undergoing occlusion, meaning the rotation within the mesocyclone was beginning to collapse on itself. This phenomenon occurs when the base of the mesocyclone closes over the funnel, cutting off its supply of warm air and forcing it to dissipate. During this process, it's common for the vortex to make erratic turns or curves before dissipating. Data collected by Doppler radar and mobile weather stations confirmed that the tornado had a lifespan of about 20 minutes, with a path length of approximately 8 kilometers. Its forward speed was between 25 and 35 kilometers per hour, relatively slow for a tornado, allowing videographers to capture each phase in exceptional detail. The official intensity, as mentioned above, was classified as F2 on the old Fujita scale. This means estimated winds of between 182 and 250 kilometers per hour. But many meteorologists and storm chasers suggest that the classification underestimates the event's true strength. Why? Because the Fujita scale, at least in its original version, doesn't directly measure winds. It assesses damage. And if a tornado passes over open countryside, with few structures to analyze, its true strength remains shrouded in uncertainty. In this sense, the Columbus tornado is a clear example of the limitations of traditional tornado classification. The damage it caused was real, but because it didn't hit densely built-up areas, its signature was underestimated. Despite everything, this tornado was not forgotten. Quite the contrary. It became a benchmark for the study of open-air tornadoes. The recordings of Sunderman, Wilkie, and especially Ulmer, have been analyzed by meteorologists around the world. Each frame was dissected to understand the evolution of the structure, the changes in direction, and the internal processes of a mature supercell. Even in 2005, when the enhanced Fujita scale (EF scale) was released, some researchers suggested that events like Columbus should be re-evaluated using modern technology and three-dimensional image analysis. After a tornado hits, the world seems to stop. The birds fall silent, the trees uprooted look like motionless sculptures, and the air smells different, a mixture of churned earth, wounded vegetation, and evaporated electricity. That's how Columbus, Nebraska woke up the day after the storm. The tornado Andy Ulmer filmed dissipated shortly after 7 p.m., just a few miles northeast of his property. What had begun as a distant funnel ended as a thin rope, spinning furiously until its final breath. Although its total path was no more than 8 kilometers, the trail it left was telling. Wind-swept fields, uprooted trees, collapsed rural structures, and farm machinery scattered like broken toys. But most importantly, there were no fatalities, not a single life lost. It was, without a doubt, a statistical miracle. Because although the tornado's intensity was officially classified as F2, with winds estimated at between 182 and 250 kilometers per hour, many experts believe its true power was underestimated. The reason behind this discrepancy lies in the evaluation methodology. For decades, tornadoes in the United States were classified using the original Fujita scale F scale, developed in 1971 by Professor Tetsuya Theodore Fujita. This scale assigned a category from F0 to F5, based solely on observed damage to human structures, not actual winds. This implied an obvious bias. If a tornado crossed a field without buildings, it could be classified as weak, even if its winds would have been strong enough to destroy a city. And that's what happened in Columbus. Passing through rural areas with few sturdy buildings to serve as a reference, the tornado left insufficient evidence of its power. Cameras showed an impressive vortex structure. Radars captured intense rotation, but the terrain couldn't speak for itself. Enhanced Fujita scale, EF scale, was implemented in 2007, incorporating more precise analyses of the type of damaged buildings and the materials used. Had it existed back then, the tornado might have been reclassified as an EF3 or even higher. However, Columbus's importance lies not only in numbers. His true legacy lies in the silent lessons he left behind. First, it clearly showed how a tornado can be extremely intense and still not leave a tragic aftermath if its path avoids urban centers. This doesn't mean it's less dangerous, but rather that chance can disguise the danger of moderation. Second, the event demonstrated the invaluable value of citizen documentation. Ulmer, Sunderman, and Wilkie's recordings complemented what radars couldn't see: the visual appearance, the vortex behavior, the sounds, the human gestures. Meteorological science was nourished not only by data, but by emotions. After the storm, Columbus residents slowly returned to their routines. Roofs were repaired, roads were cleared, crops were assessed. For many, the tornado was a non-life-threatening scare, but for others it was a reminder of how close the abyss can be even on a peaceful afternoon. Andy Ulmer, for his part, became a discreet but symbolic figure. He didn't seek fame, he didn't monetize his video, he didn't capitalize on his moment. He simply went back to work, knowing he had witnessed and chronicled something unique. And over the years, as other storms made headlines, the story of the Columbus tornado became a gem of meteorological documentary, a time capsule filmed from the heart of the threat. At the national level, the case also influenced risk communication policies. Until the late 1990s, tornado warnings were typically generic. But after events like Columbus, the National Weather Service began incorporating more visual and narrative detail into its announcements. Early warning systems were improved, sirens were installed in rural areas, and the use of weather radios was encouraged in agricultural communities. Community weather education programs teaching citizens how to interpret the sky, how to identify a supercell, and when to seek shelter without waiting for official confirmation. All of this responded to an undeniable reality. In the world of tornadoes, information can save lives. And sometimes, so can a live camera. 25 years later, the memory of the Columbus tornado still lingers in the air. Not as a tragedy, but as a warning, a sign of respect for the forces beyond our control. Because at their core, tornadoes aren't just physical phenomena. They're reminders of how fragile the structure we call civilization is in the face of an atmosphere that, at times, decides to write its own history. As global climate change alters traditional weather patterns, many scientists believe that extreme events like tornadoes, hurricanes, and torrential rains will become more frequent and intense. In this context, cases like Columbus take on new significance. They are clues to the future. How do we react to the unpredictable? Are we prepared to face increasingly violent storms? Will we know how to differentiate spectacle from danger? And will we be ready to document, understand, and endure? When the wind stops, everything seems to return to calm, but the silence after the storm is deceptive. Because even though the vortex has disappeared, its mark lingers in the landscape, in memory, in the images that survive. The Columbus tornado left no victims, but it did leave questions. And perhaps that is his greatest legacy, forcing us to look at the sky with a mixture of wonder, fear, and reverence. If this story shocked you, imagine what's still left to tell. In Extreme Tornado, we explore the deadliest vortices, the most furious skies, and the true stories that are born when nature unleashes its full power. Subscribe now and join us through every storm, because what the wind takes away, we bring it to you.